Hello friends, so let us do some more problems of our chapter work energy and power. Now here you can see that I have drawn a system comprising of a spring, and then this spring is attached to a spring, and that is passing over a fixed pulley, and the other end of the spring is attached to a block of mass m. Now this is a very standard typical system. The top ends are closely bound. Now suppose that initially we are holding this block here, so that the spring is in its natural length. So when the spring is in its natural length, it simply means just one thing, that the potential energy of the spring is zero. There is no such potential energy right now. Now, as soon as we leave this block, what will happen? Definitely under the effect of gravity, it will try to come down. So, the string has its fixed length. It means the only thing which will change its size, that is your spring. So, the spring will get elongated. Now, it's pretty clear that suppose the mass m comes down by distance x, then the spring will get elongated by distance x at the same time, because the string is of fixed length. So the only thing which will change its length is this spring. So it's been asked that what will be the maximum elongation of the spring under this situation. Now, if we take a very general look, what we will say? That up to which downward distance this mass m will go. One simple approach can be that if we just let it drop down, so there will come a point, let me use another pen, there will come a point where the downward force is mg and upward force is tension. Now what this tension is equal to? This tension here, similarly like here. So this, another end of the spring is attached to spring. It means whatever the spring restoring forces, because here is what is happening. Here the spring is getting elongated. So when the spring is getting elongated, it means there is a restoring force in the spring which actually wants it to come back to its natural position. So that restoring force will be kx. So kx will be equal to t. At the point when the net force acting on the block is 0, it means t is equal to mg. From 1 and 2, we can say that mg equals to kx. Then at this point, x equal to mg by k. Now most of us will just stop here and say that yeah, we have got the final value at x equal to mg by k. But is it correct? It's absolutely wrong. This is showing the position of x for which net force acting on block is 0. Now, we are asked that what will be the maximum elongation in this spring. How will we calculate that? And why will there be a further elongation in the spring when we have already found that at this point net force acting on the block is 0? The only thing we are missing is inertia. Because of the virtue of inertia, when the block has travelled a distance x from here to here, from position A to position B, it must have got some velocity as well. Earlier it was accelerated because during A to B, mg was greater than kx. But exactly at B, x is such that mg is equal to kx. But suppose the point up to C here. So during B to C, Kx will be greater than mg. So because of velocity, the mass will further move ahead. But during B to C, it will start deaccelerating. Because the force tension, that is because of Kx. The tension is higher than mg. So it is increasing every time and it will overcome mg, and at a point of time this block will stop. Because it is keep on deaccelerating. So please get these things very much clear here. That when it started from point A up to point B, it was accelerating. And because of acceleration, it gained some velocity. Till point B, this force was downward direction. Exactly at point B, this force became 0. Now below point B, Kx magnitude got higher than mg. So, though the block was going down, but it was actually deaccelerating at every instant. So, since it was deaccelerating, its velocity approached to 0. And at point C, block velocity became 0. So, that's why this entire x, final x, this we have to calculate. So, for that, we can do one simple thing is, when it moved down a distance, downward distance x, or you can say x dash, this we have called x, we can call this x dash. Then since it has moved on a distance x dash, so the change in potential energy, delta U, is minus mg x dash. Minus why? Because the side is decreasing. Its potential energy is decreasing. And initial kinetic energy was 0. They started from S. Final kinetic energy is also 0. So, what was the change in potential energy of the spring? This is of the block, mass m, delta U of spring. This is half A x dash square. Now, since we are considering gravity is part of the system, that's why we have included change in potential energy mgx or minus mg dash. It means we can say that total energy initial is equal to total energy final, because there is no external force acting on the system. Law of conservation of energy. If no external force acting on the system, then total energy initial is equal to total energy final. It means kinetic energy initial plus potential energy initial is equal to kinetic energy final plus potential energy final. So kinetic energy initial is 0 and potential energy initial is, we can consider 0. Let this frame be 0 potential energy, 0. Kinetic energy final, again 0. But what about potential energy final? Potential energy final is half k x dash square minus mg x dash. Because here we consider the system. So this is a part of the system, the block, as well as the spring is a part of the system. So we have to add up the change in potential energy of the entire system. So right here half a x dash square minus mg x dash. So I mean we will get half k x dash square equals to mg x dash. X dash is equal to 2 mg by, this is the right answer. The downward distance, the maximum elongation on the spring will be 2 mg by. Previous method which we have applied, that we can also solve, but it is comparatively very easy. If we will go by previous method, then what we need to do, that after going a distance of mg by k, which we calculated, that was x, we need to calculate the velocity at that point, v, and then we have to properly integrate it, because it's not a constant acceleration. The acceleration at any point of time will be ax minus mg divided by m. So it's a variable acceleration. So then we have to apply this relation which we have said earlier also, vdv is equal to ads. and then we will put the initial limit of b and final limit of 0 in position of x to x dash. This value of a we will put here, and by conservation of energy, what will the velocity at that point of time at x, that we need to calculate. We need to put it here, and then we will get the final value of x dash. So that's a much more complicated method. It will require integration as well as some proof research will be required. The easy thing is that we can simply apply the law of conservation of energy and we will solve the problem. So, for competition point of view, we don't have to look at this method. This is cumbersome. These are the easy methods. In most of the questions can be solved just by applying law of conservation of energy or law of conservation of momentum or such things we see. So I hope this is clear. Now, we'll move on the problem. Now, in this problem, there are two beams separated by height. There is a spring in between, and at the top of the spring, there is a ring attached. The ring is such that it has encircled the upper beam, so that if we drag the ring, the spring will get a shape like this. So, this length h, that is the natural length of the spring. It means a position where the potential energy of the spring is 0. Suppose somebody dragged this ring in such a way that it got a shape like this, and this angle is 37 degrees. And say like a ring has a mass m. The ring which has been attached at the top is passing through the beam that has got a mass m. So it has been dragged this way. Now the question is that suppose we let the ring leave at that point. The ring is constrained to move only along the beam. Then which direction the ring will move? Definitely in this direction. Because this was the spring's natural length, it has got elongated. So it will try to move to its natural position, so it will try to drag it this way. So the ring will ultimately come back to this position. Now will it stop here? No. We have already seen this. That by the time it will reach here, it will definitely have some velocity, inertia. So that inertia will again drag it further away. Now, we don't need to think what will happen further away. We are just asked to find the velocity at this point. That when the ring comes from this position to this position, what is the velocity at this point? So, how will this solve? It's a pretty simple problem, includes some basic geometry. The first thing to calculate is that what would be the elongation in the length of the spring. Because once we have calculated that, the problem is pretty much like just like the previous problem. So we just equate the energy. Because is there any kind of force, extra force? There is one force extra apart from the system, apart from the conservative force, there is one force, and that is the normal force between the beam and the ring. But if you just imagine a beam, if a ring is passing, the beam is passing through a ring, it just attaches at this point, and the ring is moving on the beam. So what is happening that at every point of time the normal force is actually acting in this direction or in this direction, and the motion is in this direction. So work done by normal force is always 0. Because normal force is acting perpendicular. So work done by normal force is always 0. So that makes our life very easy. Because then only conservative forces are there. The spring force and gravity. Now also, you see that gravity is also not going to play any role here. Why? Because the height of the mass, that is fixed. And spring is massless. So height of the mass is fixed, it means change in potential energy because of gravity is 0. No change in potential energy because of gravity. So the only change in potential energy will be delta U spring. So if we say what is initial potential energy, that will be some potential energy of the spring. And that's it. Kinetic energy initial is 0. We are taking this reference level as 0 potential energy because of gravity. Whatever we take does not matter. So for our convenience, we will follow that this potential energy because of gravity is 0. This will always remain 0. Now kinetic energy final will be differently something. Half mv square. Exactly B which you have to calculate. And potential energy final will be what? By the time when spring comes back to its natural length, then there won't be any factor contributing to potential energy. The spring would be in its natural length, and already we have neglected gravity because the level is same. So we can just say that UF will be 0. It means that because of EI is equal to EF, US here will be just equal to half mv square. So the only thing to calculate is the potential energy right now in the spring. And how we can calculate that? That's also pretty simple. You need to know this height. This is a right angle triangle. So what we can say? That cos theta is equal to base by hypotenuse. So hypotenuse we have to calculate. And base is what? H. H by cos 37. So cos 37 is 4 by 5. 5 is by 4. So if this length is 5h by 4 and this is its natural length, then what is the elongation? Delta x. This total length is 5h by 4 and this is h. It means the elongation in the spring is 5h by 4 minus h means h by 4. So potential energy of the spring will be half k h square by 16. That will be equal to half m v square. You cancel. You can write that v square is equal to h square a by m by 16. Means v is equal to h by 4 root under a by. So this is our result. The velocity of the ring when it comes to this position will be h by 4 root under a by. So what was anything here in this problem? There is nothing in here. Some basic geometry, very basic geometry, and again the final result. So most of the problems would be based on such conditions, like there will be no external force. You have to just make sure that there is no external force acting on the system. All the forces which are the internal conservative forces, you have to just equate the energy. That's it. And if there is any external force, you have to just add its work. So if it is doing a positive work, it will boost up its energy. EF will be greater than EI. Or if it is doing a negative work, then EF will be less than EI. As simple as that. I hope it's clear, so let's move to another problem. So this is a case in which a block is given to us of mass m. It is attached to a rod of length L, and the rod has a hook at its one end. Now below this system, this is in horizontal position. Now below this rod, there is a fixed ring at a point, and that is at a height h below the hook. Now the adjustment is made such that suppose when this system starts falling down, it will come to a position where this hook will get hooked up in the ring. Now once it gets hooked up in the ring, then what will happen? This point got fixed, it cannot move further down. It means this will follow a circular track of radius L and may also start moving up. Now, we are asked to calculate the value of height h, the minimum value actually, the minimum value of height h, such that this block completes circle and goes at the top. Now we don't know the exact value of it. I'm actually not sure whether it will reach to this point or to this point. We cannot say because we don't know whether L is greater than h or whether L is smaller than h or equal to h or whatever the relation is. We just know that it will follow a circular track and the track will definitely have a maximum height somewhere, but we don't know whatever the value of L and h is. Okay, so let's start from very basic. This was the position, consider it as the potential energy 0. So initially, no potential energy and no kinetic energy. Kinetic energy is also 0. Now just make sure, is there any external force acting on the system? There is just gravity and nothing else. So no external force acting on the system. That makes our life much easier. It means we can just equate final energy with initial energy, and initial energy is totally 0. Now, let's come to this point at height h. At this point, what is the potential energy in reference to this point? And at this point it is 0, it means at this point it is minus mg h. Force into displacement and negative. Because this potential energy is taken as 0, so definitely in reference to this position it will be taken always negative. Now, at this point, there must be some kinetic energy. Because it has fallen down. And what will be the value of kinetic energy? The kinetic energy will be such that KI at this point, say point A. KIA plus UEA, that is going to be 0. It means half mg square equals to mgh. So, V is equal to root under 2gh. So this is the velocity here, root under 2gh. So what will happen? At this point, it will start, since the other end has been moved up here, so it will start moving in a circular track. Now, when it is trying to move in a circular track, then what's going on? It will keep on moving at least up to this point, that is for sure. Definitely it will keep on moving at least up to this point under the effect of gravity. There is no question in that. Now this point is at a height L below it. Mark it. This is H, this is L, because this is the length of the rod below the fixed point here. So this is at a height L below this point. So it means that when it will come here, what will be the potential energy? That will be minus mg H plus L. So we can also calculate what will the kinetic energy be. Kinetic energy will be half m v dash square such that it is equal to mg h plus L, because net energy has to be zero. Because there is no external force acting on the system, so net energy is always zero, because initial net energy is zero. So that it will follow at every point. So from here we can calculate v dash square also. So v dash is basically root under 2g h plus L. So v dash equals to root under 2g h plus point b. So this much is the velocity or kinetic energy. Now since it has got some kinetic energy, it means it will start moving up as well. Now the question is that whether it will reach up to the maximum height or not. So let's say that if L is greater than H, just for the point, let's say, so that we can draw it like this. This dot gets doubled right here. This is somewhat upward from where it starts. Now let's say that whether it's C is possible. So we can give this name C. So at C, what will the potential energy? Potential energy at C will be mg L minus H. So this is the difference. L minus H. Up to H it was 0. So this is the 0 position. 0 position for we are calculating height from here. So this is our axis system. We are calculating our height from here. So y is equal to 0 here at this point. So at this position y will be equal to L. This is the difference from this position, because we are calculating potential energy from this frame. So potential energy will be plus, because it is at a height above it, so it will be plus mg L minus H. And what would be the kinetic energy? So just suppose that we are at the minimum risk. Means we are just letting it so that it just could reach there. The minimum risk we have to calculate. So even if the kinetic energy goes 0 there, that one we can bear. Fine, okay. If it has some extra kinetic energy, well good, fine. But even if kinetic energy goes 0, that much minimum we can afford here. As per the question. Then what has to be the minimum value of it? So for minimum, we can just afford that kinetic energy here is 0. No extra energy will go. That's why we are taking the case of minimum. Now if kinetic energy is 0, potential energy is mg L minus H. Now whether we see that whether it is possible or not. At this point, potential energy is minus mg H plus L and kinetic energy is half m v dash square. Basically just possible of that. So here you see that here net energy is not 0. If this potential energy is positive, then net energy is not 0. Because UC plus KC will be something greater than 0. Now to make it 0, KC has to be negative. Because UC is positive. Because L is greater than H. This is impossible. Because kinetic energy can never be negative. Half of V square can never be negative. It means the condition we have taken here, the assumption is wrong. So once this assumption is wrong. So let us take that L is equal to H. Then what will happen? If L is equal to H, then this will go 0. And Kc is 0. And here also total energy is 0. So this is something which we can afford. Yeah, it is possible. So from here what we got? That the minimum H should be So the maximum edge should be L. At least medium L. Or let us just check that what will happen if H is greater than L. If H is greater than L, it means the circular track would be somewhat like this. This is the height H and this is height L. So if H is greater than L, then what would happen? Its potential energy here will be what? Since it is below than this potential energy will be somewhat negative, minus of mg, L minus H. It is below it. So potential energy will be negative. It means kinetic energy will be positive. Because ultimately total energy has to be zero. Because we have started from a point. Why are we taking at every instant total energy to be zero? Because we have started from a point from where total energy was zero. So that's why at every instant of time total energy will be always zero. So this is something which is also possible. Kinetic energy can be zero. So what we infer from here? That if H is just equal to L, then this block will reach to that height and it will have a kinetic energy zero. Now if H is even less than L, if H is greater than L, then this is L and this is H. So if H is greater than L, then when this block reaches here, it will have some additional kinetic energy as well. Now what were we supposed to find? The minimum possible value of H so that the block reaches here. So what is the minimum possible value of H? It is H is equal to L. That H should be at least L less or greater than equal to, so that the block reaches here. Now just in order to explain you people, I need to take every instant, every cases. Otherwise, just in one side you can make an answer. That what was asked? What should be the minimum value of H so that the block, this track completes the circular track and reaches to this point. So forget these 2 points. Just see the initial and final point. So finally, what we are getting? Initially we know the energy is 0, total energy is 0. So at final point also total energy will be 0. And let the extreme case be kinetic energy 0 in both ends. So the only deciding factor is potential energy. So if kinetic energy is 0, then potential energy has to be same. Now when we are starting from potential energy 0, it means here also potential energy has to be 0. And when is possible? It is possible only in the case when both the locations are at the same height from the base level. It means this edge, given height H, and this rod length L, they have to be equal. Then only we'll get a solution of this step problem. Minimum value of H should be L. So, though I explained it in the bitwise manner, but the main reason behind this problem was that whenever in exam you get these kind of problems related to energy, then in most of the cases, if the system does not include any kind of non-conservative force, then in that case, we have to just see the initial and final point.